Okay, so back to diamagnetic substances. So what we said was replace them in an external field, they'll make the field weaker. They will be weakly repelled by both poles, not just a north, they'll also be weakly repelled if they're brought close to a south. Okay, so they have no net overall field. The magnetic fields of the electrons balance themselves out, no net overall field, and they make the magnetic field weaker. Examples. Examples would be good. Examples of these would be copper, bismuth, nitrogen, water, NaCl, H2, and all noble gases. So there's just a few examples of things that are diamagnetic substances. Okay, so that's one type of magnetic material. The second category are called paramagnetic substances. Paramagnetic. All right, for these guys, the magnetic fields of the electrons can temporarily line up. Okay, so they can temporarily line up, but they'll be easily destroyed. And if we were in class right now, and so I will do this tomorrow, I would take a paper clip, which is not a magnet, and I would attach it to a magnet, and once it's attached to that magnet, it begins to act like a magnet. So what happens is, when I put these paramagnetic substances in a magnetic field, they align to the field. And so they will make the magnetic field a little bit weaker. So they will make an external field weaker. Excuse me, not weaker, that's the top one. They will make an external field stronger. Okay? Not a lot stronger, just a little. But it will still be stronger. Okay? And temporarily line up but are easily destroyed. When I take that paper clip off the magnet, it won't have any magnetic effects anymore. It'll just go back to being normal. Okay? If I place them near the poles of a magnet, be it a north or be it a south, it will be attracted, weakly attracted to both. So really just the opposite. Whoops, that really is weakly attracted. Just the opposite to diamagnetic. So diamagnetic makes the external field weaker and they're weakly repelled. Paramagnetic makes the external field stronger and they are weakly attracted. But like I said, easily destroyed. And as soon as you take them off the thing that's temporarily lining them up, they will go back to just being random. Okay? Examples here are oxygen, aluminum, platinum, if you happen to be lucky enough to have some platinum, and manganese are examples of paramagnetic substances. All right, the last type is really the important one. It's the one that our magnets are made out of. It's called, number 3, ferromagnetic substances. And I suspect, I hope, that you all know that ferro is iron. Okay? So ferromagnetic substances, here, not only do the little electrons align, they all line up nice and happy, but they align up in clusters. So they align inside the atom, and the atoms align, and they form something that's called domains. And domains are clusters of atoms whose magnetic fields are aligned. Let's scratch out magnetic. Oh, I should have put a B there. Magnetic fields are aligned. Okay? Each domain can be about a millimeter in size, so we're talking significant clusters here. And within that domain, there would be a relatively strong magnetic field. And each little domain actually acts just like a bar magnet, with one end as a south and one end as a north. So under ferromagnetic substances, we actually have two categories. One category is known as non-magnetic substances, and the other category is brilliantly named, I bet you can guess it, magnetic substances. And what determines what material under ferromagnetic is which is how the domains are aligned. So inside a non-magnetic substance, the domains are what we would say would be random, right? So one might be like this, one might be like this, and then like this, and at angles. But they're random in the sense of they are not aligned in any sort of way. Okay? Whereas in magnetic substances, the domains are actually lined up. And they might not be perfect. They might not all be exactly like this. They could be, you know, at angles. But overall, they are aligned. Okay? These guys, so the aligning is like naturally occurring. Okay? These guys would be the material that we find naturally occurring in our world as magnets. But we can make magnets out of these. We can take a non-magnetic substance, put it in a strong external field, and when we do that, it causes these domains to flip around and line up. Okay? So here, before we do that, they're random and the overall fields would cancel each other out, whereas in a magnetic substance, the overall fields add up and it actually gives us magnetic material. These would be our naturally occurring magnets and our permanent magnets. You can actually mine, naturally occurring. You can actually mine a mineral that's called magnetite, and it has magnetic properties because its domains align on their own and give you a net overall field. We can make permanent magnets out of these guys. You might think you're making a magnet out of the paramagnetic, but remember what I said, they easily get messed up. But if you make a permanent magnet, if you stick this in an external strong field and get these non-magnetic substance domains to flip around, they will actually stay that way. Okay? Examples of these would be, well, the best one is iron, and that's why when it was first named, it was probably thought that it was only iron. Okay, but we know iron, we know nickel, we know cobalt, gadolinium. All of these are ferromagnetic substances. Okay? I know when I was growing up, and you maybe have seen this happen, and now we can actually buy it, but my father used to magnetize his screwdriver before he would do something. He would rub a magnet over and over in the same direction on it, and what he was doing was causing its domains to flip around. Now you can buy screwdrivers that have already been magnetized. My father should have probably patented it, but he didn't. The one thing you have to be careful about in a magnet, or two things, but one is dropping it. Because when you drop it, you jar the domains, and you can cause them to go back into randomness where they'll cancel each other out. So imagine that all these domains are aligned, and you drop it, and it jars them, and it messes them up a little. Okay, and so I have a really strong magnet that I'll let you use, but I'll caution you not to bang it, because every time you bang it, these get jarred a little. The other thing that can really mess up a magnet is heating it. When you heat a magnet, it can mess up the domains. And there's actually a temperature known as the Curie temperature where the material